Hello and welcome. Today's lesson is about the isomers. So we're going to start with something called structural isomer. What is the meaning of structural isomer? It means it's a compound, or let's say compounds with same molecular formula, but they have difference in their structure. So the difference in the structure could be in position, could be in functional group, or chain. So let's start with each one alone. So let's take the first one, which is the positional. What is the meaning of positional? So let's take an example of C3H7Br. In this case, we can call this as a molecular formula. This is molecular formula. And we just remember that the molecular formula tells me about the number of atoms in my molecule. Okay, but I don't have any idea about the framework or let's say the shape of this molecule. So let's start putting some probabilities of this compound. If I want to draw the structural formula for this compound, I can say like I have CH3, CH2, CH2, Br. So as we can see, the Br here atom is bonded to this carbon, which is carbon number 1. So I can change the position of the Br group in here. Like, why not to draw it like this? CH3, CH, Br, CH3. So in this case, the Br group is in the second carbon. So we still have the same formula, which is CH3, H7Br, but we have different structures. And the different structures appears in the position. Let's say the position of Br is in the first carbon, the position of the Pr here is in the second carbon. So we can say this type of isomers is positional because we change the position of the Br in here. So suppose that we have C, okay, and here we have Br group. So will we have any problem if we put the Br in here? Like, is it different compound or in here? Actually, you just notice that you have single covalent bond. And in the single covalent bond, you have a free rotation, okay, between C and C. So this is in continuous motion, like it can rotate freely around the axis in here, okay. So the Br here is the same as Br here and the same as Br in here. So there's no difference. You still have the same molecule in this case. So we're done with positional, and now it's time to go to the functional group. Functional group. So let's take an example of, you have a molecular formula of C3H8O. Okay, our structural isomer today is changing the functional group. So we could have two functional groups and two possible compounds. So we could have, let's say, a functional group of alcohol like CH3, CH2, CH2OH, which is a propanol. And we also could have a functional group which is called ether, and it indicates the presence of oxygen between the alkyl groups like O, CH2, CH3. So the idea of this functional group is having oxygen atom between R groups. So we call this ether. And by the way, it's not included in your class right now, but just as a functional group. So we have two functional groups. This is a family of alcohol, and here we have ether. And these are two different compounds with the same molecular formula, but they have different structures. So this is a functional group. By the way, we can take this as an OH compound, which is a propanol, and we can draw the positional functional group. Let's say we can draw the positional isomer, which means we can change the position of OH on the second carbon. So this is another idea of that. Okay, so this is the functional. You could have the same molecular formula, but they have different functional groups, different functional groups. Okay, so let's go to the last type of structural isomers, and the last type is called chain isomers. Chain isomers. Let's go and start with the first one here. Let's take another example like C4H10. So in this case, I can draw this as a straight chain, okay, and I can draw it in a branch form, okay. So if I want to draw it in the branch form, you just notice that this is alkane and appears like CH3, CH2, CH2, CH3. Okay, so this is a straight chain. Great. What about the branch form? So suppose that you're going to start CH, CH3, CH2, here, like this, yeah, CH3. So in this case, we have the same molecular formula. We have 4 carbons, okay, but one of them is a branch, okay. It has a branch in here and it has a straight chain. In this case, we have isomers. These are totally different compounds, different properties, different chemical and physical properties, as we can see. And a very good note, let's take it, which is the boiling point. So I'm going to erase all of this stuff in here. I'm going to give you another example that explains my idea well. Okay, so the idea says if you have C5H12, which is alkane, I can draw this in form of CH3, CH2, 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 CH3. So as you can see, we have 5 carbons, 3, 4, 5, okay. And I can draw this formula, okay, in other form, which is CH3, C, CH3, CH3, CH3. According to what we see, we have totally different compounds. We have compound number 1 and compound number 2. This is chain and this is branch. Okay, so what do you think about the properties that, let's say, about the boiling point, the boiling point, and let's say melting point? What do you think about these? According to what we have nonpolar molecules. So the only type of intermolecular forces is temporary dipole, induced dipole, which is van der Waals, remember that. And it's considered as a weak bonding. And we just remember, according to this type of intermolecular forces, it depends on 2 things. It depends on the number of electrons and it depends on the length of molecule. As we can see, this molecule is longer than this. They have the same number of electrons, okay? But this is longer, which means more contact points, which means stronger intermolecular forces and higher melting point and boiling point in this case. So this is our lesson. This one has higher melting point, and this is due to the contact point, stronger intermolecular forces, and that's it.